My name is Dumitriu, and I'm the CEO of Midokura. And I'd like to tell you about our SDN solution and how we're starting to use multiple Southbound protocols and a bit of the motivation for why we are so excited and so interested in OpenDaylight. So the outline of my presentation is going to start off with an overview of our company and then talking about the drivers for SDN and network virtualization in particular, which is what we're focused on. A little bit about SDN architectures and why OpenDaylight and the use cases that we're talking about addressing with OpenDaylight. And then we also have a short demo video that we've put together with one of our partners, which shows the exploitation of one of those Southbound protocols. And we'll have some room for Q&A at the end if you have any questions. So our company was founded in 2010, and we started off always focused on infrastructure as a service use cases. We started off the company in Tokyo, but we now have a presence in the San Francisco Bay Area as well, where we have some of our key members. We started off network virtualization as our core competence for infrastructure as a service cloud. And notably, we got started in the OpenStack space around the end of 2010, so it was quite early in this. And we've gone through quite a few of the evolutions of the networking paradigms there, and I think that's influenced our solution quite a bit. So our company, we received our Series A funding last year, which was $17 million we raised, fairly large Series A round that's allowed us to expand our engineering capabilities and ultimately our sales force as well here in the US. We were among the top 10 of the CRN SDN startups in 2013, and we've gotten a fair bit of traction in the enterprise as well as service provider customers. Okay. I just want to call out a couple of our customers and our ecosystem. We have Sakura Internet and KT partners. Red Hat, we're working with them very closely on OpenStack Neutron, which is our primary way that the customers consume our solution through the Neutron API and all the network services there. And we've been working within the context of OpenDaylight, in particular with Cisco, IBM, Plexi, and Cumulus on several different projects related to northbound and southbound APIs. So the drivers of SDN adoption for us are primarily infrastructure as a service cloud, which is being deployed in a lot of different situations and scenarios. Amazon and AWS really changed the way that IT infrastructure is consumed and delivered, and gave rise to what you all know as shadow IT, where basically the desire for application owners to have agility of the infrastructure caused them to go to service providers, even outside their own companies, that could actually provide that. And as that pressure has built up, their own IT departments now are looking to provide the same level of agility and control. So therefore, that means infrastructure as a service cloud, self-service IT, and more control given to the application owners, while the infrastructure operators and the security folks, they really want to maintain the policy control and the security policies that they're used to. So it's this dichotomy between agility and control that is driving large change in the enterprise IT infrastructure, and it requires changes to the network infrastructure as well in various ways. So that's where we come in. That's where SDN comes in general. So talking about SDN architectures, for a number of years now that we've been involved in this, SDN, for some people, has been equated with OpenFlow, right? So that's been the first kind of decoupling of control and data plane that's allowed some innovation to happen beyond what was happening, for the last 10, 15 years and so on. So that's great. That was a great start. But SDN for us is a lot more than just that. So in particular, SDN doesn't mean fully centralized control planes, right? It doesn't mean remotely programming fibs or TCAMs, a la the OpenFlow model. It can be a lot of different things that start exploiting, again, these multiple southbound protocols that we now start to have available. I say start because we really are just at the beginning of what can be possible. So in particular, SDN can be a combination of distributed and centralized control. The distributed control plane, routing plane with BGP and OSPF, it works. We don't need to actually change that out necessarily, but we can augment it in various ways. And certain services are actually best implemented using overlay technologies that sit on top of this type of fabric. So I'm going to talk about what is possible and why, by doing both the distributed and centralized control, we have some very interesting solutions that can come up. I'll tell you a little bit about our solution first, and then we'll talk about how it fits in with the multiple southbound protocols. So MidoNet, our product, it's a software distributed overlay solution that implements network virtualization. So network virtualization is the ability to create some familiar network constructs like layer 2 networks, logical routers, and some other higher level services like the NAT service, stateful and stateless firewalls. And all this is implemented in software in a distributed system. That overlay network sits on top of an existing IP network. And basically all of the intelligence of the system is implemented at the edge on the x86 servers, on hypervisor hosts, or other x86 servers. So far, so good. And this is what we deliver, again, through OpenStack Neutron to the users of the infrastructure service cloud. MidoNet is not a central control system, and it doesn't use like a reactive flow programming model. Therefore, it's a bit more efficient in that sense, so that it doesn't actually need to bog down a central control system. It's a very distributed approach to the control plane, if you will. So the way this actually works is, here in this picture, we actually show a couple of different systems. So at the top is what we call the network state database, which is it's logically centralized, but actually multiply distributed database service that stores the network configuration, both the static virtual network configuration, as well as a dynamic state that needs to be shared among all of the agents in the system to implement this, the functionality. The physical servers, which are basically Linux hosts running the hypervisors, they also run our agent, which is there, and it communicates with the network state database as well as with each other to share enough information to provide this distributed layer 2, layer 3, layer 4 functionality. And in the middle, the interconnect is just an IP fabric, right? So as long as we pass IP, that could be something like a CLOS network that has very high cross-section bandwidth, and it's the only requirement that the system actually has. And then for external connectivity, we use pretty much the same thing. It's a very symmetric type of model. The same agent also runs on x86 hosts to provide external connectivity outside of the cloud. And that could be either L3 or L2. In this case, for example, we show it says BGP gateway. So for interconnecting L3, we do use BGP. So we have a BGP service integrated in with our control plane so that external networks can speak BGP to our cloud, like AS to AS, and that will be fed into the routing tables and the fibs that eventually get distributed to the agents, right? So that way we actually can interoperate in a scalable and redundant way with external networks. And we also have the same model also works for L2, so we can actually plug the gateway services into your existing VLAN trunks and then map VLANs into layer 2 virtual networks inside our system, right? So this is all fairly basic so far, right? But it is the base on top of which we need to build all the other network services. And the yellow lines there are the tunnels, the encapsulations over IP, and we do support GRE and VXLAN. So VXLAN being more preferred now because it's able to be load balanced over the infrastructure. which GRE sometimes doesn't work. Right. Okay. So that's our solution, right? And the value proposition of deploying this type of overlay solution, there are a couple of different things. One is you can deploy applications and provision the virtual resources, instantly, because there's no wires to unplug. Obviously, this is all just software configuration of the system, right? So again, we can reduce the provisioning time from sometimes hours or days to seconds. It's instant. Going over the top makes a lot of sense, right? You can use your existing hardware, so we don't have to actually change any of the network out because it runs over the top. And that's a pretty good, I think, for this stage of the deployments, right? We're not talking about ripping everything out and replacing it, right? And we support multiple hypervisors and multiple cloud platforms and practically any x86 hardware. So if you're running OpenStack or CloudStack or your own homegrown platform, which some of our clients do, that can be integrated with our solution via an API and such. So that's on the management plane. On the hypervisor and the data plane, KVM, Xen, LXC, Docker, other containers on Linux, those all work. And we do also now have an integration that works with ESXi, Hyper-V in the works, right? So that can really build out a multi-hypervisor cloud as well in cases where that's required, which does happen. A lot of customers have an ESX vSphere deployment with ESX. They also want to run an OpenStack cloud, which might be the one that ends up scaling more, but critical services may remain on VMware. So the multi-hypervisor approach does have some value in that case. So overlays are great, right? We have all these good properties. However, we also do have some limitations, and those limitations start to be felt, as the deployments get bigger and more complex, and as QoS requirements start becoming more stringent. So one thing is, there's limited visibility from the operator of the overlay into what's happening in the physical network. So if traffic doesn't pass through, maybe you can't tell why, right? There's no great OAM functions in the overlay right now. So that's one thing. Software overlays are great if 100% of all your workload is virtualized, but that's not true. So certain databases or performance-sensitive services are not running in virtual machines, and that's likely to remain that way for some time. Also, QoS is a big deal, and in our initial deployments, the types of workloads that run on top of an OpenStack cloud necessarily don't have super strict QoS requirements. But as we move into other things like, for example, someone wants to run both the storage and the access network on the same physical network. Now we need to do some kind of isolation using QoS. Or another case, maybe we're talking about NFV, right, which is a huge topic that I'm not going to get into here. But if we're talking about NFV and telco voice applications, the sensitivity to jitter and latency is high. So therefore, we need to do stuff with QoS and prioritization. And we can do a fair amount of that with the overlay, but maybe not quite enough. And finally, again, the hardware switch for physical workloads is an important point because we will have some situations where bare metal clouds are actually where certain users are going. Like, for example, maybe the big data type of applications, they don't want to virtualize those. So what are we going to do? With the overlay, that's not quite enough. So enter OpenDaylight, right? Sorry, this is my joke from Enter the Dragon. So the nice thing about OpenDaylight that really was true from the very start, even before we got involved, is that there are already a plethora of Southbound APIs starting to be available. So I've listed a few here. Maybe they're not all quite there yet, but certainly they all will be there, right? Netconf, basic CLI, over SSH interfaces, SNMP, XMPP, OpenFlow, OVSDB, BGP, all of these interfaces are part of the OpenDaylight source code and code base. Almost all of them are there today. For us, as a vendor with a very specific solution, it's difficult for us to actually engineer all of these interfaces in-house, right? So we're very excited about OpenDaylight, particularly for this point. So we're going to leverage the ODP community-provided Southbound APIs and contribute to some of them as well, as needed to make enhancements to address some of the issues that we talked about on the previous slide. So for Southbound APIs are used for provisioning physical and virtual resources. In our case, particularly, we're interested in the physical ones, and allows more control by the IT and network admins. And we can use this to using QoS, we can maximize the network utilization, which is one of the points that's important for reducing cost, for example. And ultimately, using the right tool for the job is what this is about. So in the overlay case, we do our own synchronization protocol between the network state database and the agents at the edge, because it's all our software running on all of these points. However, in the case of interacting with the physical network, we actually need to use some third-party protocols as well. We need to use Southbound protocols to talk to multi-vendor network hardware and devices. So in the system that we've implemented, we actually run the ODP controller side by side with our MidoNet components, and we interconnect things at the state database level, and we leverage. I'll talk about the one use case that we're going to show a demo for today. So in this case, we interact with the hardware using the OVSDB protocol, as our protocol. So VXLAN is the emerging standard for IP encapsulation within the data center, right? VXLAN is running over this data center IP fabric. So we endorse the IP fabric within the data center rather than a pure Ethernet for a variety of reasons. The Ethernet fabrics are actually quite finicky. Some of them contain, many of them are actually very specific to vendors. So we really like IP as the base technology to build the IP fabric, even within the data center. Frankly, I'm actually a big proponent of running IP all the way to the server everywhere. And some people are actually definitely doing that with great success. The other thing about VXLAN is that it's starting to be supported as in offload. So in Ethernet chips are able to offload in cap and decap of VXLAN. And it's the whole overlay argument of it allows us to decouple the physical network from the overlay. But we use a fancier control plane than the IETF standard. So that's what we're going to talk about here. So this use case number one of using multiple Southbound protocols in conjunction with an overlay is the virtual physical gateway. So this is something that we worked on together with Cumulus networks. And we built, with Cumulus Linux running on a physical switch that's acting as the VXLAN VTEP, we built this using OVSDB. The point being, again, to interact with legacy applications that are sitting on non-virtualized servers. Without a virtual switch, there's no virtual switch. And actually, the switch itself, the physical switch, isn't a virtual switch. There's no hypervisor to run it on. So we needed a way to interact with that. So this is the architecture. So the system looks very similar to the previous one, except that next to our network state database, we've also added the ODL controller, right? And then on the bottom right is the actual hardware switch, the VTEP, and that is talking with the ODL controller using the OVSDB protocol. And then we built a module in there that is basically reading the MAC to VTEP mappings from our network state database and feeding those to the Cumulus switch. And then vice versa, it's receiving MAC to VNI mappings from the cumulus switch and feeding them into our network state database that then get distributed out to the agents so that when all these devices need to forward Ethernet frames for particular VLANs, they know how to encapsulate what VNI ID to put on those and which IP addresses of which VTEP or which virtual server to send those to. So it's actually pretty simple. It's good. Simple is good. So Cumulus Linux, as you know, it's a standard Linux operating system for Ethernet switches, which is amazing and awesome, right? So now we have an open platform that we can actually run software on the switches, which is very exciting for us. And the OVSDB interface to the switch allows us to share this information, like the MAC to VTEP mappings everywhere. The switch itself there are several vendors that are supported by Cumulus Linux, and we can get some very nice 10G, 1040G Ethernet switches to build an IP fabric in the data center. So we could use these on the top of rack switches of the non-virtualized workloads, at least, and then we put this communicates with the rest of the system via OVSDB. The switch itself can run the distributed control plane too, the IPVs for PGP, so that or OSPF, so that we can implement the fabric of the network. Okay, and now I'm going to show a video of the demo that we did together with Cumulus. So now, I hope that this is legible. Let's see. Oh boy. Oh, awesome. Okay, so I'm going to shut up for 5 minutes, and because this is narrated by one of our awesome engineers. And this is together with OpenStack, by the way. So it's an OpenStack environment that's running MidoNet and with this gateway.
Hello.
Okay.
So I'm going to record the video for the VXLAN interoperability with Cumulus. What I'm showing on the screen are 4 bits. This is a Cumulus switch where we have a bunch of physical hosts. We can also we have a physical port, a physical switch configured that has one logical switch. The logical switch has one local MAC, which this corresponds to the local end of the VXLAN tunnel. And the same thing in the remote MACs, we don't have any because we still don't know the MidoNet bridge, the MidoNet side. Here we have an IP. Here we have this IP that corresponds to a VM that is living on the cumulus side. So this is connected directly to the VXLAN, so to the VTEP, sorry. Here we have an OSDI console, so we can do operations. This is running on my laptop, so we can VTEP connect to Cumulus. This is actually going to show localhost because I'm running this on my laptop through an SSH tunnel. So we could do the same operations. We can do VTEP list ls, and we have Cumulus that matches Cumulus here. We can also do VTEP is list ls. We have this guy here that we had before. We can also do VTEP list mcast max. So we see all of them mcast max. And similarly, we can do. So we have the empty unicast tables. We can also do VTEP add ls, give it a VNI, and give it a name. So now we have a new logical switch. The nice thing is that we can do VTEP list ls, and this new logical switch already appears here. And here we can do the same thing. We can do ls, and now we have the logical switch here. If we would remove it, this guy disappears. So we have demonstrated notifications. now what we will do is we have this OpenStack dashboard. This is has a couple of VMs that are being managed by MidoNet. This guy lives on 10.0.1.3. So I'm going to connect to that VM. And once we are here, I'm going to open it, the whole screen. So we see that, oops, now, this living in 1.3 as this one is. We can show that there's no connectivity from one to the other, obviously because there's no way that one machine can get to the other. So what we can do now is come to the OSCI console, and we can do the following command. Mac. We give it an ls, which is ls0. We give it a MAC, which will correspond to this guy here. So we do FA163E3760 FB, and we give it an IP. The IP is going to be the one from MidoNet. That's corresponds to the MidoNet host. So we had this. Now we had a unicast MAC. This physical locator ID, this tells us that it's created a physical locator that maps to this IP address on this switch, corresponds to this local switch. So now we can do now we have added a multicast MAC, and we have a unicast MAC. What happens now is that we can do this, and we get a successful ping that is going from one machine to the other. It would be interesting to mention that we have a huge latency. Why is this? Because this is happening through the Atlantic. Here we can show that we actually have the same remote MACs. Note that we do have, this was before empty, now we actually populated this couple of entries, mapping to the MidoNet port. One thing we can do is clear the remote MACs on ls. And now we have broken connectivity. So that's the demo. Thank you.
Okay. So there you go. That was the demo. And some of you might have noticed there were a couple of manual commands there, to connect the switch with the rest of the overlay. That is currently being automated, I assure you. Okay. So the other case I mentioned was troubleshooting. So this is, again, the visibility issue between the overlay and the underlay, where the operator of the overlay in the cloud really wants to know what's going on when some connectivity is broken or something's slow. There's opacity there that we can't do anything about. So again, for this, we haven't built a solution for this yet, but we're working again with our partner. And we're going to be using, again, other Southbound protocols to exchange information or instrument the physical network and get information about the traffic that's being passed, that traffic that we've tagged in our overlay. Third use case is application policy. So in application policy, we may exploit multiple types of actions, including QoS application, besides service chaining and such. And app policy, as you know, within OpenDaylight is another one of these top-level projects that we're involved in to add that and create standardized models and interfaces. So for actually implementing that to enforce the QoS actions, we need Southbound for QoS configuration. Now, we could do it all by hand, but that would be extremely painful, right? Especially across a large network, and then you could never change it again. So with like a netconf type of southbound API, we can configure the traffic classes and mappings of DSCP to traffic classes on the underlay fabric switches. And in our overlay at the edge on x86, we classify and mark the traffic, like the DSCP bits in IP encapsulation. So currently, there's no standard for doing this, but ODP provides all kinds of options, and we're going to figure something out. We're going to figure something out that works, and we're going to present it here again in another session. And hopefully, we can create a de facto standard of something that actually does work. Okay. So what's needed to provide a complete solution? Our overlay network provides a lot of cool functionality, and it's very useful for the operator of the infrastructure as a service cloud. But we still need these southbound APIs to interact with the hardware so that we can implement these functions, right? Like QoS, gateways, and such. And working within the OpenDaylight project with a rich set of southbound APIs, we're going to fill that requirement. Our controller and the southbound of ODP run side by side, exchanging a lot of useful information, and we can build some very complete solutions for the network operators and the cloud operators to realize a vision where all the infrastructure is very easily manageable and provides all the right visibility. So we're not replacing our controller, but we're actually augmenting it to extend with these southbounds. That's the end of my presentation. If you have any questions, I'd be happy to take those or meet you at the booth later. And I've been asked to remind you that there's a survey that you should all fill out and for a chance to win a Nexus 7. Thank you very much.